start the recording. Okay, so last time we were talking about we talked about characters, and so we defined a character as a homomorphism from a group to the units in a field, which you can also think of as sort of giving a way to sort of let your group act by symmetries of a one-dimensional vector space. And then we talked about characters, a few examples. We talked about characters of the real numbers. We talked about continuous characters of the real numbers in the circle group. We talked about characters of Z mod NZ. And then I sort of did a heuristic, impressionistic sort of discussion of Fourier theory on the circle. So I want to start by just sort of pointing out two supplements that I didn't, things I meant to say last time, but I didn't. So two additions. And then sort of after I do that, we'll come back and we'll talk about Fourier theory on Z mod NZ, which is something where we can actually easily prove things. So the first addition I wanted to point out is if chi is a homomorphism from G to L cross, so L is a field, so a character of G, then, well, L cross is abelian. So it's just the non-zero elements of L under multiplication, but that's, I mean, a multiplication in a field is, so my definition of a field is commutative. If you're French, maybe your definition of a field is not commutative, but I don't think any of you are French, so we should be okay. So a non-commutative, sort of a non-commutative ring where everything at zero is not invertible, we usually call a division algebra or a skew field. Whereas I think, okay, well, the word core in French is sometimes used, well, this doesn't matter. The point is for us, so L cross is abelian, and so because L cross is abelian, this factors for the abelianization of G. So this factors as so factors, we call the abelianization is just G mod its commutator subgroup. So it's the sort of largest abelian quotient of G. And so any map to an abelian group factors through the abelianization of G. So this is why all of the examples I did were about characters of abelian groups, because characters of any group sort of reduce to characters of abelian groups. Because if you have a character of some group, well, that's the same as giving a character of this abelianization. So that was the first addition I wanted to make. The second addition is I somehow forgot to say what the Fourier transform is in this picture of Fourier theory, and I guess people are probably more familiar with the Fourier transform than sort of anything else, so I should have put that in here. So let me do sort of Fourier theory. We call this Fourier theory on S1, which I can also think of as being the real numbers mod 2 pi Z. Okay, and so then what is the Fourier transform? So I have some function f on S1, which I'm actually just going to think of sort of is equal to R mod 2 pi Z. So I'm sort of write my coordinates in R just using the standard fundamental domain. So I'll write sort of integration over sort of 0 to 2 pi. So I'll just write integration sort of as over a fundamental domain in the real numbers for this quotient. Then we define f hat of k to be the integral. So here k is in Z. So it's the integral from 0 to 2 pi of f times e to the minus ik. So f of t e to the minus ikt dt. So this should look, let me do over 2 pi. So this, well, if you've seen the Fourier transform before, this should look sort of something like something and this should look roughly familiar depending on what you saw. And there are different normalizations people take. And like if you we're not doing the Fourier transform on the circle, if you were doing like on all of the real numbers, you'd sort of allow any, instead of k here, like k would be a real number instead of integer. But here, the circle, we should just do integers. Okay, and I just want to point out, in this Fourier transform, and this is just a coefficient of the character, sort of t goes to e to the I kt. So it's the coefficient of this function in the expansion. So f of k, so f of t is equal to sum of k and z, f hat of k times e to the 2 pi I, sorry, e to the ikt. So in the Fourier transform is just giving you these coefficients when you sort of expand your function in terms of this sort of basis, this sort of alternative basis for your Hilbert space. I mean, this looks, I mean, I don't know, and the Fourier transform is often sort of introduced as this mysterious thing. And depending on your motivations, oftentimes the first time you see the Fourier transform is, for example, for applications to differential equations where like the key thing about it is it turns differentiation to multiplication. I mean, so when you see it in this way, like, I mean, it can sort of seem like a mysterious thing that's happening, and this is not anything mysterious at all. This is just, I mean, this f hat of k is just the inner product of your function f with e to the ikt. So the function, so these e to the ikt, these are your basis vectors. These are your orthonormal basis. And these functions f, like this function f, you're trying to express f in terms of sort of your orthonormal basis. Well, if you're trying to express a function in terms of an orthonormal basis, like the coefficients are just the inner product. So this is sort of how the Fourier transform fits into this picture. Okay, so I just wanted to point that out. Good. So, all right, but we won't do anything more with S1. We're going to focus on finite groups when we're talking about representation theory later, and finite groups when we're talking about Galois theory. So let's do some Fourier theory on Z mod NZ. So let me just recall from last time that we have, so last time we described the characters of Z mod NZ with values in the complex. So we described the complex valued characters of Z mod NZ. The characters, so we have, remember we wrote X of Z mod NZ for the set of characters with complex values. This is Z mod NZ C star. And we had that this was isomorphic to Z mod NZ, where some K inside of here corresponds to the character which sends, so let me call the variable here T. So T maps to e to the ikt times, sorry, e to the kt, so this way 2 pi I over n. So, and these are just, and this looks a lot like the characters we saw for the circle in passing. I mean, you can think of, I mean, it's not such a bad idea to think of Z mod NZ as being, and sort of if you can sort of embed Z mod NZ inside of the circle. So it's not such a bad idea to think about doing that here, just as sort of the roots of unity lying on the circle. Okay, so anyway, so we know what the characters of Z mod NZ are. Okay, and so I mean these. So let me call this chi sub k. I think that's what I called it before. So this character that sends t to the e to the kt times 2 pi I over n, this character is Z mod nz. Another way to think of this is just the unique character that sends 1 to e to the 2 pi I times over n times k. So sort of e to the 2 pi I times k over n is sort of an nth root of unity, and sort of this unique map that sends 1 to that. So I called that chi k last time, I think, and let me continue that. So these functions chi k, they live inside of just, let me just write the space of, let me just write it, so I'll write f for functions from Z mod nz to C. So these are just all functions from the finite set Z mod nz to the complex numbers. Okay, so this is, I mean, a character is in particular, and it's a function that satisfies some nice properties, but in particular, it's just a function. So this is a complex vector space. What's the dimension of this complex vector space? Oh, maybe someone wrote in the chat. Sorry, I realized I didn't open it. Thank you. Yes, the dimension is n. So this is n dimensional. Can someone give me a simple basis for this complex vector space? Yeah, so characteristics functions have been suggested. So good. So, and if any, if I take for k and Z mod nz, I can look at the sort of delta function at k. So I can look at the characteristic function of just the subset k. So this is the function whose value is 1 if k is equal to t, and 0 if k is not equal to t. So this just picks out, and this is, yeah, this is a delta function. Okay, and so, and if you have, and these are clearly linearly independent, and if you have f, so if you have some function, some complex valued function on Z mod nz, then f is just equal to the sum over all k and Z mod nz, so over all n elements of the set of f of k times delta k. So this is just unraveling the definitions to see that this is true. So that sort of shows that it spans. So these are our basis. So this is how you can see that this is an n-dimensional vector space. It's just using these delta functions as a basis. And then there's nothing special about Z mod nz here. This sentence is true if I sort of look at the vector space of functions on any finite set. So if I have any finite set, I look at the vector space of all functions on that finite set, then I can just sort of take these delta functions or characteristic functions of sort of the one element subsets, and those form a basis of vector spaces for that vector space. Are there other questions about that? Are there any questions about that statement? Did that, yes, speak now or hold your peace? Okay, so good. So this is an n-dimensional vector space, and it's actually, and we can equip it with a natural inner product. So, and for this inner product, actually, these delta k will be an orthonormal basis. So there's a natural inner product, Hermitian inner product on F from Z mod NZ to C. And so what is it? Well, we should just send, so we should send, so we should pair two functions, F and G. We should just look at the sum over all elements in Z mod NZ of F of T times G bar of T. I mean, we may, well, there are different, so we can, and you can multiply this by any scalar, and sort of depending on what you're doing, it may be useful to multiply this by a scalar. So, but for example, if we didn't multiply this by a scalar at all, then this delta k, these delta functions will form an orthonormal basis, and they're sort of that easily seem to be orthogonal. So delta k are an orthonormal basis. For this Hermitian inner product. And this is just, again, sort of straight from the definition. Just write this out. And so and this is just like the inner product you take on like L2 functions on the circle, or L2 functions on anything. You're just summing up over a finite set. Like, well, a finite set, sort of the natural measure on a finite set is just sort of the sum of the point measures. And so we're just summing up over a finite set is integrating over that finite set. So when you have a finite set, like this is really L2 of Z mod NZ. So all functions are L2 functions. So if you know, well, anyway, so if you know what L2 functions are, and last time was a useful lecture for you, then maybe this is a useful observation. Otherwise, just ignore that. Okay, so good. So we have this Hermitian inner product, but I'm actually going to normalize it slightly differently. So I'm going to normalize it by dividing by n. So actually, let me write F comma G for just, so I'll write parentheses for the inner product I want to use. So I'm going to divide it by the size of the group. And we'll see why in a second. Because well, we'll see. And the reason why is because I want the following theorem to be true. So the characters chi k are an orthonormal basis for F Z mod NZ C. Sorry, for this space equipped with the inner product FG, the inner product with parentheses. So where I take the sum by divide by n. In another way, so taking the sum and dividing by n, that's Haar, like that's sort of the normalized Haar measure. So like this is sort of like the probability, or another way to say this is the probability measure on this. So the total space has measure 1 with respect to this measure, where you divide by n. Okay, so mean, what do you, and well, sort of, what do you have to do to check this? And you just have to check that they're, okay, so let's do the easiest parts first. Wait, you just have to check the like to see that it's orthonormal basis. You just have to check that it's orthonormal because there are the right number of them. So there are sort of n. There are n things. So there are n functions chi k and chi sub k. These characters that we were writing down earlier. Let me just scroll up to the definition. So chi k was this function that sends so t to e to the kt times 2 pi I over n. There are n of these chi k, and good. There are n of these, and so it suffices to show they're orthonormal. So an orthonormality implies linear independence. And so if you have n linearly independent functions in an n-dimensional vector space, they're a basis. So this n is equal to dimension of the vector space. Okay, and so good. And so now let's first check that they're sort of the normal part of orthonormal. So we need to check, and we have two things left to check to see they're orthonormal. So first, we need to check like sort of chi k let me say chi k1, chi k2 is equal to 0 if k1 is not equal to k2, and it's equal to 1 if k1 is equal to k2. Okay. So let me make an important observation for this. So in this inner product, what we're doing is sort of we're taking, like, you're summing up the product of the two functions, like the function on the left and the complex conjugate of the function on the right. So an important observation in this computation is that chi k, if I take the complex conjugate of this function, so this just means sort of chi k bar of t is the complex conjugate of chi k of t. Well, this is equal to just chi k inverse. So that means if I take the inverse of every, and this is bad notation, well, okay. This does not mean inverse is like inverse as a function, the inverse function. This means sort of take the values of chi k and then sort of take the reciprocals, which makes sense because this is sort of non-zero. So let me write this as actually as 1 over chi k. Which is equal to chi minus k. So, and what is the point? Well, chi k bar of t is by definition, so the proof of the observation, well, this is by definition just chi k of t, then bar that. Well, this is e to the 2 pi I k t over n. So let me write this how I wrote before. So it's the e to the kt 2 pi I over n, complex conjugate. But I mean, this is the standard identity. In the complex conjugate, when you sort of take e to something purely imaginary, the complex conjugate just sort of flips it around. So it's e to the minus kt 2 pi I over n. So complex conjugation on sort of e to the something, it doesn't change the real part and sort of just flips the imaginary part in the exponent. Minus kt. That's right. That the flip side there's a minus sign. And the point is sort of rotating by like, if I rotate by theta and then flip about the, yeah. So if I'm like in the complex plane and like, or I rotate by theta, and then I flip about, I reflect about the x origin, that's the same as rotating by minus theta. So this is like, and this is like the kind of computation you do when you're working in the dihedral group. So this is sort of not so bad. Okay, so, and then this is sort of chi minus k of t. And so, yeah, and just another, and if you haven't thought about, well, depending on what you've been up to, you might not have thought about the complex numbers in a while. So if you haven't thought about the complex numbers in a while, and just one important thing to remember that's always true is that if you start with something on the unit circle in the complex numbers, then conjugation is the same as inverse on the unit circle. Because sort of x, like z times z bar is just the absolute value of z squared. So if the absolute value of z is 1, then z times z bar is 1. That's sort of why this is also the reciprocal. Okay, so when we're computing then this inner product, oops, it should have been the parentheses inner product, not the brackets one. So the parentheses one was the one I normalized. So chi k1 inner product chi k2, this is just the sum over all t in z mod nz of chi k1 of t times chi k2 bar of t all over n. So this is the sum over t containing z mod nz, chi k1 of t times chi of minus k2 of t for n. And now the characters themselves form a group. So it's not so hard to check. And this is something we already discussed last time, but chi k1 times chi, like chi k1 times chi minus k2, that's just chi of k1 minus k2 of t over n. So this inner product of these two characters, it's actually just, you're adding up the values of some other character and dividing by n. So suffices to see that sort of the sum over all the values, if you add up all the values of a character, then this is going to be equal to, so we want k1 minus k2 to, if k1 minus k2 is not 0, then sort of this thing should be 0. So this is going to be 0 if k is not equal to 0, which sort of corresponds to k1 minus 2, k2, k1 not being equal to k2 above. And this should be n if k is equal to 0. Okay. So good. So and this is, part of this is really easy. And if k is equal to 0, then this is just a trivial character. So in this case, so chi sub 0 of t is just equal to 1 for every t. So check. So yeah, in this other case, you have to sort of think a little bit. But so this other part, like, so to see this, you need to see, and essentially you reduce to, for any m, the sum of the mth roots. So for any m not equal to 1, so any m larger than 1, the sum of the mth roots of unity in C is equal to 0. So this is not, I mean, this sum will not always be of this form. You have to think a little bit about what's going on. and this sum will always be like some multiple. Like this sum that's showing up here is always going to be some multiple of sort of the sum of all mth roots of unity for some m. So like the thing is like if n is equal to 4, then you can sort of write down a character such that when you sum it up, you're sort of summing up over all second roots of unity, but you're doing it 2 times. So and there's some step in the reduction to get to this, but then this is the key point. And this is a simple but important identity. It's really obvious. I mean, the picture is obvious. And so like the picture is just you have all these vectors, and they're supposed to be canceling each other out. I mean, I've drawn the case where like this picture literally proves it, because so when n is even, then sort of for any root of unity minus that root of unity is also an nth root of unity. And so like here you can literally cancel out these two. The odd case, that picture doesn't work. So in the odd case, like n is equal to 3, you have this sort of force diagram from your physics classes. But these force, like if you sort of apply this force diagram, you can test it out on with whatever pulley system you ever rigged up at home. So that was a bad joke. And these 3 vectors sum up to 0 as well. And if you can write down the formulas for the third roots of unity and like just check with cosines and sines. It's like standard things that this works out. But there's a better way to see it than sort of trying to do it sort of ad hoc. So just for any m, and the product. Okay, so if I look at product from k is equal to 0 to m minus 1. I look at the polynomial x minus e to 2 pi I k. over m, sorry. Well, I mean, we discussed last time, these are all of the mth roots of unity. So I'm taking the product over x minus all of the roots of mth roots of unity. So these are all the roots of x to the m minus 1. So this is just the factorization of x to the m minus 1. And so, but now the coefficient of x to the m minus 1 is just the sum of the roots, or is equal to minus the sum of the roots. And so that sort of holds for any polynomial. Like the coefficient, you can just expand this out. The coefficient of x to the m minus 1 is just minus the sum of the roots. So this is minus the sum of all of the mth roots of unity. And this is equal to 0 unless m is equal to 1. Otherwise, it's 1. But of course, the sum of all the first roots of unity is 1. Are there any questions about this statement? Okay, good. So, yeah, okay. So this once you have this fact is easy. It's an exercise you should do it if you haven't thought about this before. But it's not so hard to see that sort of the sum over all the values of this character when this character is non-trivial just gives you 0. But that's exactly the computation that tells us this is the computation we had reduced to see that these characters were an orthonormal basis. Okay, so we sort of finished the proof that these characters form an orthonormal basis for functions on Z mod NZ. Okay, and so what this means, just like Fourier analysis on the circle, is if we have a function from Z mod NZ to the complex numbers, then we can write it as just the sum from k equals 0 to n minus 1 of f hat of k, and let me sort of, anyway, it's sum over all k in z mod nz, so fix and represent. So f hat of k times I chi k, where f hat of k, well, I mean, we can write down a formula for it, but this is just the inner product of f. So this is supposed to like the Fourier transform again, but it's just the inner product of f of chi k. So this is, and again, whenever you, and hopefully this is not unfamiliar to you, but maybe you're possibly you're rusty with this fact, but whenever you have an orthonormal basis, like the coefficients when you expand some function that with some vector in that basis are just given by the inner product. Like that's sort of, that somehow that's the point of an orthonormal basis. Okay, so what is f product of pi chi k? Well, this is just the sum from k, sorry, from over t and z mod nz of f of t times chi k t bar, which if you expand it out, this is all the sum over all t contained z mod nz of f of t times e to the minus kt times 2 pi I over n. Okay, so just like, I mean, again, so looks just like the classical Fourier transform. Oh, and then divided by n. Okay. So this is sort of, I mean, this is a fun toy example where you, I mean, somehow the nice part about this example is you sort of get Fourier analysis without doing any analysis, because when you're working on this finite group, like all of the analytic issues with like defining which space you're working with, like looking at L2 functions, those sort of go away, and all like, and so if you're an analyst or if you take a class in analysis, so from an analyst perspective, and somehow I've gotten rid of every interesting part of Fourier analysis, which would sort of be like the questions about sort of and relating regularity and sort of Fourier coefficients and so, yeah. So and there's sort of a whole interesting analytic theory of Fourier analysis on the real numbers that like I've suppressed here by going to the final. But on the other hand, like this isolates sort of this example, and this isolates sort of what's really going on sort of somehow from a algebraic perspective. And you just have this nice basis of characters that you're using for your functions instead of sort of like the delta functions. Yeah, so, okay. Let me sort of make some remarks. And this generalizes easily to any finite abelian group. And finite abelian groups are all just products of cyclic groups. So, and somehow, once you understand what Fourier analysis is on sort of a cyclic group, it's not too, and you, once you, like, for example, once you know the characters of cyclic groups, and you also know all the characters of products of cyclic groups, and again, you can show and you can define an inner product the same way and show things to define base. It's not much harder than this is sort of the point. And so you get sort of the exact same statements. Like the characters of any finite abelian group form an orthonormal basis for like the natural inner product on functions on that abelian group. Something more interesting, and I think we'll probably, and not today and not for a long time, but at the end of the class, we'll spend some time talking about the generalization to, so this generalizes to finite groups, to all finite groups. Okay, and it generalizes sort of also like the compact groups like S1. It generalizes to non-compact groups in a much more like interesting way, much more interesting and difficult way. We won't talk about that at all. But in particular, it generalizes sort of to finite groups. But then, and for finite groups, you can't look just at sort of one-dimensional representation. You can't look at characters in this sense. So here you sort of need higher dimensional representation theory. So you need to think about it, not just how your group can act as sort of symmetries of a one-dimensional vector space, but how your group can act as symmetries of like a two-dimensional vector space or a three-dimensional vector space. But once you have that, you can sort of give a generalization of this Fourier decomposition. Okay, so that's a couple of remarks. Let me make one other observation that's related to an observation I made at the end about Fourier theory on S1 last time. So the space of functions on Z mod NZ, this has an action of Z mod NZ. So I'm going to take the right translation action. Okay, so what that means is sort of if I take some element K in Z mod NZ, and then I sort of hit it with I attack some function with my element K, and then I evaluate the new function I'm supposed to get at T, this is just equal to F of T times K. Okay, and so what's interesting about this action and sort of what we've done before is so for each, so now I'm using a lot of Ks. Okay, let me write J up here just so I don't have sort of too many Ks. So I'm rewriting the element of Z mod NZ that was acting on a function as J, just so because I was sort of indexing my characters with the letter K, and I'm about to talk about characters. So for each character, well, let me just say, I won't put a subscript here. I'll just put K, or I'll just put chi. So the span C times chi, so this just means the one-dimensional subspace spanned by chi, contained in Z mod NZ. This is preserved by the group action. So in this group action, this right translation action, it respects the vector space structure. So this is an example of what I mean when I say a higher dimensional representation. This is this is an n-dimensional vector space that sort of has an action of this group, and so that's literally what I mean by a representation of a group. It's just a linear, like an action on a vector space by linear transformations, and that's exactly what this is. Good, but then what I'm saying is that there are these subspaces inside that are preserved by this action, which is sort of, okay, and I'll explain this, why these are preserved in a second. It's just a simple computation, and let me point out this is sort of interesting from the theory of group actions, because I mean, you can think of this action, like this action on this vector space, as coming from just the right translation action of Z mod NZ on itself. So like Z mod NZ acts on itself by right translation. So this is like an action of a set. And that action is irreducible. It's like Z mod NZ is its own orbit, like is a single orbit under right translation. So like somehow if you just think about like the group action of Z mod NZ on the set Z mod NZ, like that's indecomposable. It doesn't break down to smaller chunks. But if I sort of linearize by sort of, instead of looking at the set itself, I look at sort of complex valued functions in the set. Now what I'm claiming is that there are like, this thing is no longer sort of irreducible. Like there are sort of smaller components I can break it into. So this is like a one-dimensional subspace that's preserved by the group action is an example. I should point out, so this action is unitary. So a unitary action, that just means it preserves the Hermitian inner product that I wrote down before. So what that tells you is and what that means concretely, I'm not going to, and we'll come back to this later, so I'm not going to do it now, but and we'll come back to this when we actually do representation theory. But the point of unitariness here is that if I know some subspace is preserved, then I know also its complementary subspace is preserved. That's the key thing it gives you. Okay, and in here we won't need that to sort of see what I want. So this C times chi, well, why is this preserved? Well, it just comes from the identity that's sort of for J times chi of T. This is equal to chi of T times J. But chi is a character, so this is just chi of T times chi of J. Let me just write that as chi of J times chi of T. So this holds for all T, so J times the action of J on chi. So J acting on this function by right translation just sends it to chi of J times chi. So now this is a complex number, and this is sort of just taking the complex number and multiplying it by this vector. Like this vector is just getting scaled by this complex number chi of J. Okay, so another way to think about this is like what I'm saying here is sort of so for each J in Z mod NZ, I get some automorphism of this space, of this vector space. Saying that automorphism preserves this one-dimensional subspace is saying that sort of, and this is an eigenspace. So like chi is an eigenvector. This function chi, which is sort of just a vector in this vectored space, is an eigenvector for the automorphism coming from sort of right translation by any element J. And so you have this, you have this vector that's sort of simultaneous. You have these vectors are simultaneous eigenvectors for everything. And again, if you've done some function, so I mean, somebody stop me if no one knows any functional analysis. Do you get Okay. Well, anyway, but somehow, and this should be familiar if you do know some basic functional analysis. Like this is just this isn't surprising. This is, you have these unitary operators this is a commuting family of operators, for example. And like, so in spectral theory, like it's not surprising that a commuting family of operators like has a simultaneous eigenbasis. It's sort of the kind of thing you see. Okay, so okay, but anyway, so what this means is like this basis. So the basis chi1 through or chi. So the basis chi k for k contained in Z mod NZ. So it gives a decomposition. So this, and one way to think about this is functions from Z mod NZ to C. So another way to say you have a basis is to say like you have a decomposition as a direct sum of the one-dimensional subspace spanned by each of those basis elements. So this is the direct sum of the subspaces okay. So this is just the one-dimensional subspace spanned by this vector. And so each of these, like this decomposition is preserved by the action of Z mod NZ. So Z mod NZ is acting on these functions by right translation. And we just computed that it was preserving sort of each of these one-dimensional subspaces. So, and this is what I'm saying, like this sort of magical thing happens. It's a very powerful magical thing that happens where like Z mod NZ acting on itself by right translation had a single orbit. But now when I look at I linearize and I look at space of functions on it, now this is built up like of smaller irreducible chunks corresponding to the characters of your group. And so this is something we'll see more generally in representation theory. When we do this at the end, there'll be a notion of an irreducible representation, which is a representation that has no sort of proper sub-representations. And every representation of a finite group on a complex vector space will sort of break up as a direct sum of irreducible representations. But sort of in this interesting way that really for example, enriches the theory of like G sets with G action in the sense that if you sort of take a finite set with a G action, like even though that set itself might have a single orbit, the vector space you get from it can sort of break down into smaller chunks. And this is a very powerful idea for various applications. Okay, so that's one thing I wanted to observe. Let me also make a further observation. There's a natural way to write down the projections. So the projections are just sort of given by the Fourier coefficients. But let me write that down. Actually, let me say it this way. So exercise. This is related to something that comes up on your homework, which is why I want to point it out. So if chi is a character of G, and so rho is a map from G to V is a complex vector space. So chi is a complex valued character of G, and rho is, well, representation. So it's a map just to GL, like to the GLV. So GLV just means invertible linear transformations on some vector space V. So you write this when you don't want to write down, like when you don't want to fix a basis. And so then, sort of if V is a vector in this vector space V, then we can make a new vector. We can look at just the sum over all G and G of, and now I'd better do this carefully, right? So this should be chi of G inverse. Let me say it this way, and 1 over chi of G, which is, and you can write it as chi of G inverse or chi of G bar, or whatever you prefer, times rho of G times V. Let's sort of call this B sub chi. Satisfies the rho of G acting on V sub chi is equal to chi of G times V sub chi. So, and if you write out this formula in the case we're looking at, in sort of the case of functions, like you're just going to recover sort of like formula for the projection onto the. So this formula is just going to give you projection onto sort of this character space, the space spanned by sort of the corresponding character, and it's going to look basically the same. Like if you expand this out in this example we're looking at, where V is sort of functions from Z mod NZ to C, what you're going to see is you're going to see some other version of writing down the Fourier coefficients. So, in general, what's going to happen for an arbitrary representation is you can sort of break it down into irreducible representations. Some of those representations are going to be one-dimensional; those correspond to characters. And this is exactly going to sort of give you sort of the formula for projecting onto, like doing the orthogonal projection onto that sort of character space. So it's somehow the point is Fourier theory in this context is really just about sort of you take this space you have, so functions on Z mod NZ to C. This is a specific space, but it's just some space with an action of Z mod NZ. then you sort of decompose it into sort of these irreducible subrepresentations, which here correspond to these characters. And then like after you do this decomposition, then you can sort of rewrite any function just to sort of using the resulting direct sum decomposition. The point is sort of this generalizes to any group, and in particular, to sort of any representation of any group. So there's actually sort of nothing special about, there are some special things, but this idea of sort of doing Fourier theory on Z mod NZ or on the circle, like in the end, it's actually this idea of like taking a representation and decomposing it into its sort of irreducible chunks. And like this is when Fourier theory is about when you do this for sort of a particularly interesting representation. So like the space of L2 functions or some function space, but you can do this for any representation, and it's useful to do it for other representations too. So in particular, on the homework that's not due till like the end of March or till the middle of March, you'll see some other example where you sort of use this projection formula to like study just like a problem in arithmetic. Okay, so that's all for now, and this is all for now on this topic, on like sort of one-dimensional representations, characters, and sort of how it ties into various things. Again, just a reminder, this isn't going to be on the exam on the midterm next week, and somehow it's just really, and it's just a preview, like it's a preview of things we'll be talking more about at the end of the semester. So there are a couple of reasons it was natural to do this preview now. One of the reasons is this last theorem I want to say. So this is independence of characters. That we actually will use in our, in Galois theory. Which says sort of if G is a group, and so G is really just any group, not necessarily a finite group, not necessarily like a topological group, just sort of any abstract group. And L is a field, and here L is just any field. So it could be the complex numbers, it could be the real numbers, it could be the rational numbers, it could be Z mod PZ, could be like, take the fraction field of like C brackets XY mod Y squared is equal to X cubed minus 1. So of any field. And chi1 and chi k are distinct characters of G with values in L, then they are linearly independent. So you have sort of some set of distinct characters, linearly independent. And what do I mean? Sort of in the space of sort of functions from G to L. So this is an L vector space. And here it's really just all functions from G to L. So we basically saw this in like the very specific example where G is a finite group. And like the argument we gave above was sort of some specific example of independence, whereas you just, and when we showed these the characters of Z mod NZ were orthogonal, all the characters of Z mod NZ were orthogonal. So we were in particular really showing they were linearly independent. But sort of this applies much more generally. It doesn't sort of use anything. Like you don't need to use orthogonality to get this. And this applies in settings where you don't sort of have such an option. So, and concretely, that just means if A1 chi1 of L sub of G plus A2 chi2 G say n chi n or A k chi k of G is equal to 0. then so here the AI. So for all G and fixed A1 for all G and G and fixed A1 through AK and L, then I'm just writing out the definition of linear independence. Then A1 is equal to A2 is equal to so on. AK is equal to 0. And a function being 0 is the same as sort of being 0 wherever you evaluate it. So that's sort of just, this is what it means for this function to be 0. It's 0 for all G, and then, well, if this is 0 for all G, this is a linear combination of these sort of things. And saying they're linearly independent means the coefficients have to be 0. This is an expansion of that. Okay, and so, well, the proof is really simple. It's just a trick. Okay, so suppose not, and then sort of take a sort of linear dependence. So if they're not linearly independent, then there is a linear dependence involving as few as possible. So this is a useful argument oftentimes for sort of establishing linear independence in this kind of setting. If you have some things you want to prove they're linearly independent, well, you can sort of start off assuming a minimal linear dependence relation. So that means like then there might be a linear dependence relation that sort of involves all k vectors, but there might also be one that involves k minus 1 vectors, and so I'm going to take one that involves k minus 1 vectors, and sort of I can sort of always find because k is a finite number, like I can always find a relation of linear independence, a linear dependence relation involving as few as possible, and then just by reordering and renumbering. And I can assume that this is of the form. So non-trivial just means like the number, and this is the number involving as few chi-k as possible. And when you have a linear dependence relation, it only really involves the ones where the coefficient's non-zero. So here it's about which coefficients are 0. So reordering and renumbering, let me just assume that I have A1 chi1 plus that plus AK chi k equals 0, and sort of A1 equals A2, or sorry, A1 through none of these AI are equal to 0. So I can assume this, and there's sort of no shorter relation. So like any dependence relation has all of the AI not equal to 0. Okay. Okay, and now, so once you've done this, then, and how these proofs go is you then get a contradiction by sort of manipulating your situation to produce a shorter dependence relation. So you sort of say a shorter non-trivial dependence relation. Okay, and so, well, how do we do that here? Well, right, so we have, so let me just fix, how do I want to do this? We have A1 chi1 E plus AK chi k of E. So E is the identity element. This is equal to 0. And so this implies that if I sort of act by right translation, So let me say it this way. Sorry, I always. Okay, A1 so plus AK is equal to 0. And then, sorry, what do I want? Yeah, sorry, let me say it this way. So, so A1, this thing is equal to 0. I'm going to get something new that's equal to 0 out of this. So for any G in G, I also get then that sort of if I apply G, so G is acting by right translation. So like G dot chi1 is just evaluated T as chi1 of T times G. So the same right translation action we were looking at before. Okay. And so, but this is equal to A1 times chi1 of G times chi1 plus AK times chi k of G times chi k. So this is exactly the computation we did before. So let me just sort of, like when we were doing C mod NZ, we did this computation. When we were working C mod NZ, we did this computation when we sort of saw that each of these character spaces was preserved. So it functions from G to L, like this has an action by right translation. So I just sort of send F. So for F in here, I say G dot F is equal to F at T. So G dot F at T is equal to F of T times G. This has this action by right translation. And if I take a character, then so G dot chi, so if chi is a character, then G dot chi of T, this is chi of G times T, which is sorry, chi of T times G. But and characters multiply, so this is chi of T times chi of G. So this means G dot chi is equal to chi of G times chi. Okay, so that's what I'm using here. I'm using this sort of, if I take the 0, like so I'm saying like this function is 0. This is a function on G, and it's 0. It's a 0 function. And then if I take the 0 function, and I hit it with right translation, well, I still have the 0 function. It doesn't matter how I translate around. Like if the function is 0, the function is 0. And so so this identity holds. This is sort of just expanding out by linearity, what it means to do the right translation action. But then like G dot chi1, the computation I just did above and that we did earlier for Z mod NZ, is chi1 of G times chi1. So now chi1 of G is a constant. This is an L, and chi1 is still this function. So maybe I should put in parentheses just so you can see these are constants in parentheses, and then these are functions that aren't in the parentheses. So this is and so this 0 over here is the 0 function. And so I guess this is something that you may or not be accustomed to, but okay. When I write 0, I mean the 0 vector inside the sort of vector space of functions. Okay, but good. So now let me choose. Yeah, actually, well, probably it's good to leave it as an exercise at this point. So get a contradiction, because we're out of time anyway. And the point is now, so I started with one linear independence, and now sort of for any G, I can get a new linear independence. And then I just have to use sort of one other piece of information I have to show that like I can get sort of these two linear dependence relations I can sort of combine to get another shorter non-trivial linear dependence relation. So and I want to do something like subtract one off the other. So you should just think about sort of what you need to do in order to get a in order to guarantee that, in order to now get a shorter non-trivial linear dependence relation, which will give you a contradiction. So exercise by using this to produce a shorter non-trivial linear dependence. Okay, so I'll stop there. Again, sorry about getting started late today, and thank you all for your patience. And I'll stick around if people have any questions.